Hi all, I am here with my new video on chemical periodicity. Let's start. In this video, we are going to learn about variation in behavior among the elements in the periodic table. Variation in metallic behavior among the elements in the periodic table. When we proceed down the group, metallic character increases. When we proceed across a period, metallic character decreases. Elements show metallic properties when they have low first ionization energies and relatively few electrons in their valence levels. Therefore, we expect that the greatest metallic character would be displayed by elements located in the lower left part of the periodic table. The least metallic character would be displayed by elements located in upper right part of the periodic table. These variations are borne out by the heavy metal non-metal line in the periodic table. Its zigzag shape is shifted further to the right as we move down the table, indicating that metallic properties appear in elements that lies further down in the table. Variation in atomic radius among the elements down a group in the periodic table. When we proceed down a group, the radii of successive atoms increase. The explanation of this increase lies in the fact that as the period increases, new principal energy levels are being occupied. Therefore, the outer electrons of successive atoms are further away from the nucleus. Additionally, the inner electrons serve to shield the outer electrons from the attraction of the nucleus. These two circumstances lead to an increase in radius. For example, elements down group 16, atomic radius of oxygen atom is 65 picometer, while atomic radius of sulfur atom is 127 picometer. Variation in atomic radius among the elements across a period in the periodic table. As we proceed across a period, the radii of successive atoms decrease. The explanation of this behavior lies in the fact that with each successive element, the positive nuclear charge increases, as does the negative electron charge. Since the successive electrons are being added in the same principal energy level, the force of attraction between the nucleus and the electron increases, leading to decrease in radius. For example, elements across period 3, atomic radius of Na atom is 190 picometer, while atomic radius of magnesium atom is 160 picometer. Variation in first ionization energy among the elements down a group in the periodic table. As we proceed down a group, the first ionization energy decreases. As we know that the first ionization energy is the energy needed to remove one electron from the atom. If the electron is loosely held, the first ionization energy is low. If the electron is tightly held, the first ionization energy is high. There is an inverse relationship between the radius of an atom and its first ionization energy. The larger the radius, the more weakly its outer electron is held and consequently the more easily it is removed. Example, elements down group 16. First ionization energy of oxygen atom is 1314 kJ per mole, while first ionization energy of sulfur atom is 1000 kJ per mole, which is lesser than oxygen atom. Variation in first ionization energy among the elements across a period in the periodic table. As we proceed across a period, the first ionization energy of successive elements generally increases. For example, elements across period 3, first ionization energy of Na is 496 kJ per mole, while first ionization energy of magnesium is 738 kJ per mole. We conclude from this observation that elements located at the left side of the periodic table and elements located towards the bottom of the periodic table have the greatest tendency to lose electrons. Variation in electronegativity among the elements in the periodic table. As we proceed down a group, electronegativity decreases. Elements located successively further down a group have a decreased ability to attract electrons. As we proceed across a group, electronegativity increases. Elements located successively to the right across a period have an increased ability to attract electrons. Additional aspects of first ionization energy. An atom can have as many ionization energies as it has electrons. Successive ionization energies can become very large because of the considerable difficulty in separating negative electrons from increasingly positive ions. When an atom has all the valence electrons removed, the removal of the next electron requires the absorption of a very large quantity of energy. Because these electrons lies Within the noble gas core of the atom, such electrons are tightly held by the nucleus of the atom. Explanation of the irregularities of aluminum. The explanation for the irregularities of aluminum lies in the fact that the outer electron is in the 3p sublevel. As a result, this electron has more energy and therefore less energy is needed to remove it from the atom. Explanation of the irregularities of sulfur. The irregularity of sulfur is explained by the fact that its outer electron is the fourth electron in the 3p sublevel. Removing this electron will leave a half-filled 3p sublevel that has more stability. This removal requires less energy than removing a single electron in phosphorus, which has already half-filled 3p sublevel. As a result, the first ionization energy for sulfur is less than phosphorus. These observations allow us to state an important principle. Half-filled and fully filled sublevels provide an atom with additional stability. In our next video, we are going to learn about the chemistry of the representative groups. So please like and subscribe to watch new videos. Bye bye for now.